Hey everybody, welcome to lecture number 9 in Calculus 2. We're going to be talking about the area function in this lecture and probably the next 2 lectures also. Here's the description of the problem. Given 2 continuous functions, f of x and g of x, with f of x greater than or equal to g of x over the interval AB on the x-axis, compute the area bounded by the graphs of f of x and g of x between x equal a and x equal b. Now let me draw attention to some of the things that are mentioned here in the statement of this problem. First of all, we have 2 continuous functions, f of x and g of x. What do we know about continuous functions? The graphs of continuous functions have no breaks or interruptions. They're just one long piece of spaghetti, one long connected piece. Continuous functions that we know about are polynomials. All polynomials are continuous. Sine and cosine are continuous. E to the x is continuous. Natural log of x is continuous on the open interval from x equals 0 to x equal infinity. Sums, differences, and products of continuous functions are continuous. Take 2 or more continuous functions, add, subtract, multiply them together, you get another continuous function. Quotients of continuous functions are continuous at those points that don't cause division by 0. So if we have the quotient of 2 continuous functions and the denominator is never 0, then that's a continuous function also. So we have 2 continuous functions, f of x and g of x. Their graphs have no breaks, no interruptions, just one long connected piece of spaghetti. And f of x is greater than or equal to g of x. And what that means is that for every value of x in this interval, the graph of f of x is going to be above the graph of g of x. The graph of f of x will never dip below the graph of g of x. So let me draw a picture of what these words are describing. Let's look at what we have. Here's the graph of f of x, no breaks, no interruptions. Here's the graph of g of x. And you know, I could have done this a little bit better. I apologize. Oh, that looks a lot better. Here's the graph of y equals g of x, no breaks, no interruptions. It's one long connected piece of spaghetti. And notice that the graph of f of x lies above the graph of g of x. So f of x is greater than or equal to g of x. And we want the area bounded by the graph of f of x and the graph of g of x between x equal a and x equal b. So this is the region whose area we want to compute. That's our goal. And you know, it's kind of a lofty goal. That we have a lot of area formulas from geometry. let's see, triangle, 1/2 the base times the height. Rectangle, length times width. We can compute the area of a pentagon. We can compute the area of a hexagon. Most of the geometric figures whose areas we can compute, if we think about it, are geometric figures that bound an area with line segments. There's probably only one formula that we know from geometry in which the region whose area the formula gives is not bounded solely by line segments, and that's the area of a circle. The other areas from geometry that we know, they're all the areas of regions that are bounded by line segments. So here we're doing something cutting edge as far as our mathematical experience goes. The top of the region is bounded by a graph that's not a straight line. The bottom of the region is bounded by a graph that's not a straight line. And we certainly will progress to the point where the entire region is bounded by graphs that are not straight lines. We will be computing those areas too. So this is going to take us beyond our past mathematical experience, because with the exception of a circle, the only areas that we know how to compute are the areas of regions that are bounded by line segments. So let's see how we're going to do this. Here's how we're going to do it. This is the Caveman Method, the hammer and chisel method. And believe it or not, it's a method that we want to be able to perform ourselves, because we're going to use this method for applications other than area problems. The first thing we do, graph the bounded region. And I will say this, and I can't emphasize this enough. Anytime that we do an area problem, the first thing that we do is graph the bounded region. We don't ever do an area problem without graphing the region first. It's going to turn out that we'll learn a few different ways to compute the area of this bounded region, but regardless of the method that we use, we always graph the bounded region first whenever we do an area problem. That's always our first step. Now, our second step, partition the interval spanned by the region into n subintervals of equal length, and we'll call the length of each of these subintervals delta x. And this b minus a over n, what is that? Well, think about it. Here's the interval spanned by the region from a to b. What's the length of this interval? Well, let's do a quick example. What's the length of that interval? It's a horizontal distance, right? You know the length. It's 9 minus 3 equals 6. Now, how did you get it? Didn't we take the larger x coordinate and subtract from it the lesser x coordinate? That's how we got the length of the interval. Let's go back and look at this interval. What's its length? It's a horizontal distance, so the length is just the greater x coordinate b minus the lesser x coordinate a. B minus a, this is just the length of the interval from a to b. So we're taking the length of this interval and we're dividing it by n, the number of subintervals. And that will give us the length of each subinterval, which we call delta x. Let me draw these subintervals. Okay. And each one of these subintervals has a length of delta x. So that is our second step. Third step. In each interval, we have n subintervals for I equal 1, 2, 3, all the way up to n. Pick a point from the ith subinterval and call it x of I. Pick any point in that subinterval. In the first subinterval, I'll pick a point here, call it x of 1. In the second subinterval, I'll pick a point here and call it x of 2, and so on and so forth. Here's the ith subinterval. I'll pick a point and call it x of I. And then in the nth subinterval, I'll pick a point and call it x of n. From the first subinterval, we pick a point, call it x of 1. From the second subinterval, we pick a point, call it x of 2. From the ith subinterval, we pick a point, call it x of I. And from the nth subinterval, we pick a point and call it x of n. Oh, now what? For I equal 1 to n, we inscribe a rectangle of width delta x over the ith subinterval. And we do this in such a way that the top of the rectangle contains the point x sub I, f of x sub I. And the bottom of the rectangle contains the point x sub I, g of x sub I. And at this point, I think I'm going to erase part of the board and draw a much larger picture of that graph. Okay. Over each interval, I'm going to draw a rectangle of width delta x. And the top of that rectangle, for I equal 1, will go through the point x sub 1, f of x sub 1. The bottom will go through the point x sub 1, g of x sub 1. And then we do the same thing for the second subinterval. We picked a point x sub 2. We inscribe a rectangle of width delta x over each subinterval. Yep. Well, I'll do it this way. Each of these subintervals has width delta x. This is the point x sub 2, g of x sub 2. This is the point x sub 2, f of x sub 2. And this will be the point x sub 3, g of x sub 3. X sub 3, f of x sub 3. Here in the ith subinterval, this will be the point x sub I, g of x sub I. This will be the point x sub I, f of x sub I. And we continue on in this fashion. Until we reach the nth subinterval. There we did it. And before we go to step 5, we're going to make an observation that will motivate our step 5. Here's a key observation. The rectangles, when stacked side by side, form a region whose shape and area are approximately the same as the bounded region whose area we wish to compute. These rectangles here, if we put them all together, they form a region that looks very much like the bounded region whose area we wish to compute. And clearly, the areas of these rectangles, if we add them up, is going to be approximately the same is the area of the bounded region that we want to compute. So here's what I suggest. I suggest a compromise. Instead of trying to compute the area exactly, let's just add up the areas of these rectangles and approximate the area of the bounded region. Let's do that. So here's my idea. The area of the bounded region is approximately equal to the area of the first rectangle, plus the area of the second rectangle, plus the area of the third rectangle, plus dot, 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 plus the area of the ith rectangle, plus dot, 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 plus the area of the nth rectangle. If we add up the areas of all of these rectangles, we get approximately the area of the bounded region. Let's tidy this up a little bit. Let capital A be the area of the bounded region. And for I equal 1, 2, dot, 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 n, let A sub I equal the area of the ith rectangle. Then we can rewrite this approximation this way. Area of the bounded region is approximately equal to area of the first rectangle plus area of the second rectangle plus area of the third rectangle plus dot, 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 plus area of the ith rectangle plus dot, 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 plus area of the nth rectangle. Does this look vaguely familiar to something that we just learned about? And if you're thinking summation notation, yep, that's exactly what I'm getting at. We can approximate the area of the bounded region using summation notation this way. The sum from I equal 1 to n of A sub I, where A sub I is the area of the ith rectangle. And oh, you know what? We won't stop there. We'll do a little bit better. Just hold on. Now let's actually compute some of the areas of these rectangles. Let's go to the first rectangle. Here's our first rectangle. And all of our rectangles have width delta x. So the width of this rectangle is delta x. What's the height of this rectangle? And realize that we're computing a vertical distance. The height of this rectangle is the distance from here to here. How do we compute a vertical distance? Let's see. What's the distance from 3 to 9 on the y-axis? It's 6. And how did we get it? We took the greater y-coordinate and subtracted from it the lesser y-coordinate. Now, let's apply this to computing the area of the first rectangle. The width is delta x. The height is the distance from here, where the y-coordinate is g of x of 1, to here, where the y-coordinate is f of x of 1. So isn't the distance going to be isn't the distance going to be the greater y coordinate, f of x of 1, minus the lesser y coordinate, g of x of 1? It sure is. So this is the height of our first rectangle. And the width is delta x. So let's do this one or two more times. Second rectangle. The area of the second rectangle. The width of this rectangle is also delta x. And this rectangle goes from a height of, well, this rectangle, the height goes from g of x of 2 to f of x of 2. The height of this rectangle is the difference of the y coordinates. The greater y coordinate, f of x of 2, minus the lesser y coordinate, g of x of 2, this is the area of the second rectangle. Now let's generalize it. Let's do the area of the ith rectangle. The height of the ith rectangle, what is it? Isn't it the greater y coordinate minus the lesser y coordinate? F of x of I minus g of x of I. Okay. I want to take this and modify my approximation of the area of the bounded region. Area approximately equal to the sum from I equal 1 to n of the area of the ith rectangle, that's f of x of I minus g of x of I, delta x. This is my approximation for the bounded area. Just recapping where we were, we established that the area of the bounded region is approximately equal to the sum of the areas of the rectangles that we inscribed in this bounded region. And it seemed like a pretty good idea. There's one thing I'm kind of upset about. I think I probably could have done a better job of approximating this bounded region if I had exercised some foresight. Here's what I'm talking about. Some of the rectangles, the tops of the rectangles poke through the graph on top, and they include area that's not really part of the bounded region. And same thing down here. So some of these rectangles include area that they shouldn't include. And I will fill these regions in with red. These are regions that we shouldn't be including in our approximation. On the other hand, sometimes there's some area that actually is bounded by the graphs of f of x and g of x that isn't contained in any rectangle. Look at this area right here. It's not contained in any rectangle. This area is not, this area is not. This area is not contained in any rectangle, and it should be. A lot of the rectangles contain area that they shouldn't, and some of the rectangles don't contain area that they should. And I can identify part of the problem, and I'm going to write out what I think part of the problem is. I'm not going to talk about a solution. I'm just identifying the problem here. Here's our observation. Our approximation is not good because some rectangles contain area that they shouldn't. Other rectangles don't contain area that they should. And now here's my observation. This is a consequence of the fact that the tops and bottoms of the rectangles don't conform precisely to the contours of the graphs of f of x and g of x. And how could they? The tops and bottoms of our rectangles are straight line segments. They're not going to conform precisely to the contours of our graphs, which are not line segments. So the tops and bottoms of the rectangles don't conform precisely to the contours of the graphs of f of x and g of x. Nevertheless, we can still probably improve the accuracy of our approximation. I ask my students this: what could I have done using essentially the same method? What could I have done to get a better approximation? And usually when I ask them this, they say, well, if you made the rectangles thinner, and that's a good observation. Make the rectangles thinner. Well, the width of each rectangle is delta x. So what they're really saying is make delta x smaller. And if we make delta x smaller, if we make these rectangles thinner, won't we need more rectangles to fill up this region? Equivalently, make n the number of rectangles larger. And typically, this is what my students tell me. When I ask them what I could have done to get a better to get a better approximation. Make the rectangles smaller, that is, make delta x smaller. And as a consequence, the number of the rectangles in increases. Now I'm going to ask you another question in just a second. Here's what we concluded. To get a better approximation, make delta x, the width of the rectangles, smaller. And as a consequence, n, the number of the rectangles would increase. At this point, I ask my students, okay, what do we do to get an even better approximation? What do you think? When I ask my students this, they shrug their shoulders and then say, I don't know, make delta x even smaller. And my response to that is, it worked once, it ought to work again, right? So to get an even better approximation, make delta x, the width of the rectangles, even smaller. And as a consequence, the number of rectangles that we have is going to increase some more. And then I ask my students another question. I ask my students, to get the best approximation, what are we going to do? And they say things like, well, what do you think, first of all? What should we do to get the best approximation possible? I'd like to hear your thoughts, really. Sometimes my students say, well, make delta x, the width of the rectangles, as small as possible. And others would say, make delta x equal to 0. And then they stop and they think, wait a minute, oops. No, if we make delta x 0, that means that the width of each of these rectangles will be 0. And that means that the area of each rectangle will be the height times the width, which is 0. The area will be height times 0. The area of each rectangle will be 0. And we're just going to be adding up a bunch of rectangles that have 0 area. So they say, we can't actually make delta x equal 0. But we do want to make it as small as possible. And I'll ask them, well, how small is that? Well, make it as small as possible. And I say, okay, we want to make delta x, the width of the rectangles, as small as possible. But at the same time, we can't make the width 0. And then somebody would say, you know, we want delta x to be as close to 0 as possible, but not equal to 0. And I like that answer. And when I hear that, I say, okay, we want delta x to get closer and closer to 0, but we arbitrarily close to 0, but we don't ever want it to actually get there. What mathematical process are we talking about? And they say the same thing that you're thinking right now. The limit. Let delta x approach 0, but not actually get there. We're going to compute the limit as delta x approaches 0. And this is great news, let me tell you. You know, we thought we were going to have to settle for an approximation, but if we compute the limit as delta x goes to 0, it's no longer an approximation. We get the exact area. Area is the limit as delta x goes to 0 of the sum from I equal 1 to n of the height f of x sub I minus g of x sub I delta x. And I should acknowledge something. Typically, when I write this down, I just write delta x goes to 0. But as the width of the rectangles goes to 0, what's happening to the number of those rectangles? N? N's going to infinity, isn't it? So parenthetically, we'll note that as delta x goes to 0, n goes to infinity. Okay. Now, how do we compute something like this? We can do it directly. We can. We don't want to. I'm a pretty brave fellow, but I don't think I have enough courage to compute this thing directly. It can be done. Remember back in Calculus 1, when we were computing the derivative using the limit process, and we had the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And even computing the derivative of a function like x squared, which is a pretty simple function, even computing the derivative of a function like x squared was not completely trivial. It involved more work than we wanted to put in, which is why we came up with formulas for derivative, like the power rule and so forth. And oh my goodness, can you imagine how hard it would be if we actually computed the derivative of something like sine x or cosine x using the limit process? F of x plus delta x minus f of x all over delta x, and we let delta x go to 0. Oh my goodness, if we did that with sine or cosine, that would take forever. And if we did it for secant and tangent, things like that, oh my goodness, that would be cruel and unusual punishment. We can compute areas this way. We don't want to. And especially we don't want to when there is a fairly easy alternative. The first step that we're going to take toward an alternative way of computing this is to define what an expression like this actually is. Expressions of the form sum from I equal 1 to n, f of x sub I delta x, and sum from I equal 1 to n, f of x sub I minus g of x sub I delta x. Expressions that look like this or that look like this are called Riemann sums of order n. So we call these things Riemann sums. Well, that was a big help, wasn't it? I guess maybe we have to put in a few intermediate steps before we can compute this thing the alternative way. To take us a little bit closer to where we want to go, we're going to define the limit of a Riemann sum. And we're going to define that to be the definite integral. And I did want that dE to get in there also. The definite integral of f of x, denoted integral from x equal a to x equal b of f of x dx. We define the limit of this Riemann sum to be the definite integral of f of x dx from x equal a to x equal b. And this definitely deserves a couple of remarks before I go any further. Now, we probably have done definite integrals already, but in case we haven't, I'm going to make a few comments on this. Given the definite integral of f of x from x equal a to x equal b, x equal a and x equal b are called the lower limit of integration and the upper limit of integration, respectively. And here's an important point. Remember early on we took the interval from a to b and we partitioned it into subintervals of width delta x. The lower limit of integration and the upper limit of integration are the endpoints of the interval. That we partitioned into subintervals. Now, for an area problem, that just means that they're the endpoints of the interval that's spanned by the region whose area we're computing. But for other applications, this criterion may be the only criterion that actually works. This criterion works for all integration problems. The lower and upper limits of integration are always the endpoints of the interval that we partition into subintervals. Always, always, always. In area problems, that turns out to be the endpoints of the interval spanned by the region whose area we're computing. But for other exercises, work exercises, and things like that, we have to rely on this criterion. Now, probably we already know how to compute this, depending on the sequence of topics in our calculus courses. but maybe we don't. So that's what I'm going to talk about next. But before I talk about that, I'm going to mention one other thing. One thing that the definition of definite integral tells us is that if we compute the limit of a Riemann sum, and I may be committing mathematical blasphemy here by simplifying things to this extent, but essentially this involves a result from the fundamental theorem of calculus. And when we compute the limit of a Riemann sum, magic happens. The summation sign magically turns into the integral sign. X of I magically turns into X. Delta X magically turns into dx. And the lower and upper limits of integration are the endpoints of the subinterval that we partitioned into, the lower and upper limits of integration are the endpoints of the interval that we partitioned into subintervals. Now we'll get on to the rest of what the fundamental theorem of calculus tells us. Okay, here's what the rest of the fundamental theorem of calculus tells us. If capital F of x is any antiderivative of little f of x, then the definite integral of f of x from a to b is computed by taking the upper limit of integration and plugging it into capital F of x, taking the lower limit of integration and plugging it into capital F of x, and subtracting one from the other. Now let's do an exercise or two. Here's our little f of x. Sometimes we call this the integrand. And the fundamental theorem of calculus says that in order to compute this thing, the first thing that we have to do is to compute the antiderivative of little f of x. And it can be any antiderivative. And I'll tell you the significance of that in a second. The antiderivative of 3x squared is x cubed. The antiderivative of 6x, let's see, that's 6x squared over 2. So that would be 3x squared. And the antiderivative of 9 is 9x. Now here's where the fact that we can use any antiderivative of little f of x comes in. Since we can use any antiderivative of little f of x, why don't we use the antiderivative that doesn't have a constant term? The constant term is 0. It'll just simplify things a little bit. What this means is that if we're computing a definite integral, we don't have to add the plus c here. Well, what happens if we do add the plus c? If we do everything else correctly, it won't matter. The plus c essentially will just cancel itself out somewhere else down the line. So here is our antiderivative, capital F of x, and we're choosing the antiderivative of little f of x that has no constant term, a constant term of 0. And we are going to evaluate this from x equal 1 to x equal 3. And we plug in the upper limit of integration first, the lower limit of integration last. Plug in x equal 3, the upper limit. So here's the antiderivative evaluated at the upper limit. Now we compute the antiderivative evaluated at the lower limit. Plug in 1, we get 1 cubed. Plug in 1, we get 3 times 1 squared. Plug in 1, we get minus 9 times 1. And this is 27. This is 27. That's minus 27. So we have 27 plus 27 minus 27 is just 27. Minus this mess. 1 plus 3 is 4. Minus 9 is negative 5. So we have minus a negative 5. Okay, that concludes the first part of our lecture. Well, that concludes the first of our lectures in Cal 2 having to do with area. Our second lecture will pick up where we leave off here. We'll compute several bounded areas using the method that we just developed. And there will be a third lecture also.